Started. If you have any questions over the exam, please take the time to come by my office, or after class I might have a couple of minutes. But we're going to move on. All right, we're going to continue.
Oh, I'm so sad.
We are starting. I don't have any of the data on that test with me. I didn't send an email out or anything that said like what the class did or anything. I'll try and get a summary of that and send it out. So we're gonna start a new chapter today. Chapter 7. Chapter 7. We're going to start Chapter 7, applications. So we have spent most of this semester just figuring out how to find antiderivatives, right? I mean, that's pretty much, and we suffered through Chapter 6, all the different techniques. And now we get to see how we use these techniques to do some applications. There's a lot of different things you can do with integration, but here's just some of them. And this chapter is very visual, all right? There's a lot of geometry involved. There's a lot of graphing involved. So I would recommend that if you have a graphing calculator, that you bring it to class from here on out. Make sure you have it, learn how to use it. Instead of just having one sitting around that you paid $80 for, you may as well learn how to use it. Not required, but it will help you during a test to be able to graph things and verify what you think is happening. The first section is areas between curves. Now, I want to just remind you, because we did have a spring break, so you may have forgotten just about everything, that the whole idea here of the integral was motivated from this idea of taking some function f on some interval ab and somehow determining the area under this graph. So we did this by creating a rectangle. Wow. Rectangle. That's supposed to be a rectangle. And if we kind of come over here and look at that rectangle on the side, here's my x-axis, right? Then the width of the rectangle we said was dx, right? It was an infinitesimal width. The height of the rectangle was f of x. And so the area of that little piece was this times this, right? And then if we add them all up, that's the integral, right? Remember that connection to the Riemann sums? So this integral, a to b, f of x dx, would represent the area of the entire region. So all we're doing now is we're looking at the area between two curves. So instead of the area below a single curve all the way down to the x-axis, we want to look at two different functions and find the area between them. So not a lot is going to change here if you think about geometrically what's happening. Let me get a red one in here. If I were to want the area, let's say between another function here, which I'm going to start it at the same point. They don't have to be at the same point, and make it come, let's say, to here. So notice on the left side, they hit each other at this point, but on the right side, they don't. They just both stop at B, understand? If I want the area between those, how could I find that? Like if I want the area between these. You subtract the red one from the black one, right? So you basically could find the area under the black one first and subtract the total area underneath the red one. That difference would be the area, correct? Now that is correct approach, but I'd like for us to look at a little bit different over here, right? So what I'm going to do, let me erase this blue rectangle in here. Now, the reason why I want you to look at it a little different is because of where we're headed, all right, and what we're going to be doing here next class for sure, maybe today. So if I'm trying to find that area, then what I could do is, again, try and come up with some formula over here, right? An integral to represent like a Riemann sum. So let's draw a rectangle in here. Our rectangle this time that we want to add up only goes from here down to here. Do you agree with that?
Yeah.
We only want that rectangle added up in a bunch of them, infinite number of them. So if I translate that picture over here to the right, here's my x-axis, right? Here's my x-axis. That rectangle looks like it would be sitting about, I don't know, somewhere about here. Agreed?
Yes.
It's lifted up off the x-axis. And then the top of this rectangle will always be touching the black function, won't it? Even if I slide this rectangle to the left or to the right, the black function is like the upper bound of that, isn't it? And the lower bound of that rectangle will always be the red function, right? Understand this picture? So the top function we'll call f, the bottom function g. So tell me about, first of all, the width of this rectangle. It's still dx, right? Because what we're doing is we're moving this rectangle left and right, yes? Actually, you could say we're going to start at A and we're going to just start moving across with rectangles. The x is what's changing. So my x, the width is always your change in x. So that's still dx. The only difference is the actual height of this, which is that distance. So what is that distance? You just told me a second ago what it was. It's the f of x minus the g of x, right? It's whatever this height is, which is f, take away this height, which is g. So like if f was 10 and this was 7, then the difference would be 3, correct? So this will always be f, I'm just going to write f minus g. Is that all right? So then what's the area of this little rectangle right here? F minus g, right, times dx. And I want to add these up, right? I want to add them up. And I want to go from A to B. So your formula, now I could put f of x and g of x if I want to be a little more, change my notation a little bit more just to stress that f and g are functions of x. That's what we get, right? And that's what this formula here says. This first note for today is that if we are looking to find the area between two functions, we're going to need to know which one of them is on top and which one of them is on bottom, aren't we? We're going to need to know the top one and the bottom one. We're going to need to know A and B. We're going to need to know how to subtract these. And that's it, right? Integrate. Now I put a little note on here. I say here vertical rectangles. So notice that in my drawing, the rectangle that I draw is vertical. That's because what we're about to do after this is look at things that are no longer functions of x. And so our rectangles are no longer going to be vertical. So anytime you have a vertical rectangle, when you're trying to add these up, this is the formula we're going to use. Okay? Now let me see if I have an example ready to go here. I think, I'm going to do that example. All right, a little bit bigger here. All right, let's do this. And I would like to not look at the graph yet. So can you all see that? Sketch the region bounded by these two curves. So sketch the region bounded by these and find the area. So find area of the region bounded by y equals 2 minus x squared, and y equals negative x. So now what we're going to do is we're going to start pulling from college algebra. We're going to start pulling from pre-cal, from Cal 1. We need to know how to graph things quickly and efficiently so that we can get good pictures, so that we can get our information down and make sure our formula is correct. So hopefully you're familiar with what these two look like. This is it's a parabola. It opens down, and actually the 2 has the effect of moving it up too. So I know kind of what that looks like. And then this one, y is negative x, is just a negative diagonal. So a rough sketch of this would be something like this. This is a very rough sketch. I know it goes up to, I know that goes down like that, right? And then the other one, the diagonal, would look something like, oh, I can't draw a straight line for my life today. Like this. And let me extend this parabola down. They hit somewhere down here, don't they? So I want to know the area of the region bounded by both of those. There's only one region that's bounded by both, right? You could also say that these two curves, they enclose a region, right? So everyone see it? It's right here. We want that area. So what we're going to need to do this is we're going to need to know this point right here, because that's going to give us our A, right? We're going to need to know this point over here, because that's actually going to give us our B. And then when we draw our rectangles in here, now get into the habit of drawing the rectangles because, again, of where we're headed with this. My rectangles can be drawn like this. I'm drawing an arbitrary rectangle in here. And if I move this rectangle left and right, the black function will always be the top bound, right? And the blue one will always be the bottom. And that's what you need in order to make this formula work. You need to be able to move this rectangle all the way through this region, and that never changes. The black's always on top, blue's on bottom. Is that going to work then? Yes?
Is there a function where it won't work?
Yes. We'll look at another example in a minute. Okay, so everything look okay? You can tell from this one which is on top and which is on bottom, right? This one up here was y equals, I'm going to call this f of x, which equals 2 minus x squared, right? I'm calling it f because we were using f and g in the previous picture. F is the top one. And that means the bottom one here is y equals, which I'm going to call g of x, is negative x. So you kind of have some options at this point. Do you want to set up the integral now, do f minus g, or do you actually want to go find what a and b are first? It's your call. I don't care. A and b? You want to find a and b first? Okay. So how are you going to determine what a and b are?
Set them equal to each other.
Set them equal to each other, right? You're trying to figure out where these two graphs touch, which means the two functions are equal at that point. So, or at whichever points they're equal, right? The x values. So to find the intersection points, I'm going to set f of x equal to g of x, which means I set 2 minus x squared equal to negative x. And what type of equation is that? Quadratic. So why don't we move everything to one side? And it's our lucky day because that factors, right? Factors to be x minus 2 times x plus 1. And that gives us two solutions, doesn't it? 2 and negative 1. I think it's obvious which is which, right? A is going to be negative 1. B is going to be 2. So I actually know this is negative 1. I know that this is 2. You can put equals if you want there. Equals negative 1. We good?
Yep.
Okay. So now, at this point, we set up the integral. The integral will be integral from negative 1 to 2 right? Of, now be careful with the way you do this. It's the f function, right? Take away the g function, dx. Agreed?
Yeah.
Now in this particular problem, it's not going to be that big of a deal because the g function is only one term, right? But if g had multiple terms in it, this negative would have to distribute through, wouldn't it have to? Yeah. Right? So f, I'm going to put here 2 minus x squared. G is actually negative x. So the negative is going to become plus. And then integral -1 to 2 of 2 minus x squared plus x dx. And that's it. We're there. So now we just do what we were doing before. Let's see. Antiderivative is 2x minus a third x cubed plus a half x squared, -1 and 2. So we're using the evaluation theorem now, right? Antiderivative, 2 endpoints, and then we get to plug in. Now, what I would like to see when you do this is that you don't go to your calculator. You just try and get everything and get the exact answer. So let's plug in 2 first. So what happens when we plug in 2? 4. 2 cubed is 8 times negative, so -8/3. And then 2 squared is 4. Half of that is 2, so plus 2. And then minus. Now you plug in -1, so just be careful here. -1 times 2 is -2. -1 cubed is -1, but then times -1/3 is positive 1/3. And then -1 squared, we get plus a half. Distribute the negative through. So we have this equals, let's see, I'll just write them all out. 4 minus 8/3 plus 2 minus a third minus a half. 4 and 2, right? 8. -8/3 minus a third is -9/3, which is -3. Minus a half. 8 minus 3 is 5. 5 minus a half. 9 halves. Common denominator, 5/1, 10/2, subtract.
Yeah. That's the area between the curves.
That's the area between the curves. 9 halves. Questions? Now, on your next exam, which will be, I think, the day after the drop date? No, the week after the drop date, yeah. On your next exam, I will ask you to do something like this and actually get a numerical answer on maybe 1 or 2 of the problems. The rest of the problems will just be set up the integral, which means you're going to get it to right here, and then you're going to stop. But the problems are going to be more involved. They're going to be a little more complicated. So it's all about, can you get the integral set up? The integration we can do. It's just too time consuming. All right? All right, so let's see now. Where are we going to go from here? Oh, here, well, there was the picture. This one, let's look at example 2 and see if we can get this one going. Same thing, right? Sketch the region, find the area. But now we've got y is root x. We've got y is x minus 2. Y is 0. We actually have 3 curves now. See if we can find the region bounded by these. I would wait until you know which one's on top. Right? I mean, if you're going to stick with F and G, like F being on top of G all the time. If you want to stick with that convention, then you're going to need to wait. If you don't care and you don't mind putting G in front of F, then you can label them now. So I'm going to start with a picture, okay? Root X, we know what root X looks like. Let's see if I have enough colors to do this. Root X looks like this. This is y equals the square root of x. And then y equals x minus 2. It's a line. It's got a slope of 1, shifted down 2. So if I go down 2 on the y-axis, and I draw a diagonal like this, it's going to go that, and it's going to go this way. So far, have I enclosed a region yet?
Yes. No.
No, right? Imagine, have you ever seen like on those software programs like Microsoft Paint where it has a paint bucket? I don't know if you've ever used it, where you can like click and like it'll fill with paint. If you clicked in here and tried to fill this with color, it would come out right here, right? Yeah. The x-axis is not part of our, well, it's about to be, but if it's just these two, then there's nothing stopping, there's nothing enclosing this. Got it? But then look at the last one, y equals 0. Y equals 0 is the x-axis. So this one right here is y equals x minus 2. So this is y equals 0. Now there's a region that's enclosed by all of them, right? The region we're interested in is this one in here. We want this area. Does anybody see an issue that we're going to run into that's not going to be good?
A, B. There's multiple points? Like A, B, and C?
Okay, so would everyone agree that it starts here? Yes? If we move to the side, this would be like the ending point? Yeah? But there's something else happening, right? Do y'all see it right in here? Right. Remember I said that when you draw a rectangle and you move that rectangle all the way through, you have to have the same function on top and bottom the whole way through. Are you going to have that happen? Yeah. Depends on where I draw the rectangle, right? If I draw the rectangle over here, then the red is always on top of the green. But that has to be able to slide left and right all the way through the interval. If I were to draw that rectangle over here, it's changed now, hasn't it? The red's still on top and now the blue's on the bottom. So how do you think we can approach this? We can split it, right? We can split it into two integrals, couldn't we? We could actually split it right here at this point, figure out what that is, do one integral that gets you that area, and then do a separate integral that gets you this area, and what's going to change in them are the limits of integration, and the top and bottom functions will be different. Well, the top one will always be the red one, but the bottom one here is green, and then the bottom one here is blue. Understand? Yes?
Why does it have like 4? Or...
Then you have 4, break it up.
Yeah.
All right? We good? Yeah. So let's see if we can do this. Let's find the points of intersection first. Let's do it that way this time.
0, 0.
Okay, so that one you can tell just by looking, right? There's no work that needs to be done here.
The second one, 2, right? That would be 2.
That would be 2 because you know where that hits, right? But do you agree you're setting the green and blue ones equal to each other here?
Yes.
So you're setting this equal to this. You're setting x minus 2 equal to 0, which is x is 2. But you could just get that by inspection. This last one, you're setting the blue and the red one together, which is these two, right? So for intersection, the only one I really need to do work on is the square root of x equals x minus 2. Four works, right? 4 works just by looking. But we have to have a way of doing it, right? We need a method. And that's why in college algebra we call this a radical equation, or root equation. How do you solve root equations? Isolate the root first. So that root is isolated. Square both sides. So I'm going to square both sides at this point. I get x is x squared minus 4x plus 4. What did I do on the right side there? I actually FOILed it out, right? It does not become x squared minus 4. It doesn't become x squared plus 4. It's x squared, x minus 2 times x minus 2. This. Now you're back to a quadratic equation, right? Move everything to one side. If we're lucky, it'll factor. We're lucky. Minus 5x plus 4, x minus 4, x minus 1. Do you agree?
Yes.
Right? And so what are our solutions? 4 and 1. Wait a minute. What about 1? Hold on. What? Right? What? What? Huh? That's right. Good. Because I squared it, I introduced the possibility of extraneous solutions. That was something from college algebra. Anytime we square an equation, we always have to check our answers because there could be an answer that doesn't work. And 1 doesn't work. So if I go back here and plug in 1, right, I get what? Square root of 1 is 1. 1 minus 2 is negative 1. See, when you square both sides, that negative 1 on this side becomes a positive 1, and then they are equal. So this is an extraneous solution, which means x is 4 is our only other answer. So this is x is 4. Okay? All right. Let's set up two different integrals. The first integral will go from 0 to 2. It'll be, let me see if I can get you into the habit of doing something like that. That's going to be f minus g. So in the first integral, which we could, if you want, you could label this, all right? Like we could call this integral 1. We call this integral 2, all right? In integral 1, which is this one, what is the top function? It's just root x, right? Root x minus, what's the bottom function? 0, right? The green one, 0. I erased it, but it's 0. Whatever that area is, we want to add to that, right? Add, because we're adding up two areas. Another integral, this time it'll go from 2 to 4, and then I'm going to have a top one minus a bottom one dx, like that. So top one was still root x, bottom one x minus, what is it? X minus 2, yeah. And then when we distribute the negative, it'll become negative x plus 2. So we have integral 0 to 2 root x dx plus integral 2 to 4 of root x minus x plus 2 dx. And those, I mean, those problems right there, I hope you look at those and say, man, I wish those were the ones on the test last time, right?
This time.
Not all of them.
All right, so the antiderivative of root x, antiderivative,
It's 2x.
2/3 x to the 3 halves, evaluated 0 and 2, right? Plus, now this one's got a couple of things in it. It's going to be evaluated 2 and 4, right? So notice I kept my plus here. Antiderivative of that, well, we just did that. 2/3 x to the 3 halves minus a half x squared plus 2x, and then 2 and 4. And now it's just plug and chug. Ugh.
So like on the test, you're saying we get to this point or the point above it?
If it's a problem like this, I'm probably going to ask you to go the whole way, because these are easy enough to do.
Yeah.
But later on, it's just going to be more about, are you getting the formula right? Because, yeah. Because if you don't have the integral right, there's no sense in... All right. I would like to see what this is. I don't like these numbers, though. You'll see why I want the answer here in just a second. All right, so let's remember, when we do this, it's going to be something minus something, right? Plug in 2 first. 2 cubed is 8. Square root of 8. Is that okay? 2/3 times square root of 8. Yes, I know you can simplify that a little bit. Is that all right?
Yeah.
Minus, now plug in 0. 0, so I don't need that. Plus, now let's plug in 4. What is the square root of 4? 2 cubed? 8 times 2, 16 divided by 3. 16/3 is the first term I get. Plug 4 in here. 4 squared, 16. Half of 16 is 8, negative 8. And then 4 in here is 8. Ooh, that's nice. Those are going to cancel. But then I have to say, remember, this was just plugging in 4, right? Then I have to say minus, now plug in 2. So minus, let's plug 2 in. So what happens when I plug in 2 here? Ah, I just did that a second ago over there, didn't I? I know that's 2/3 root 8. And then when I plug 2 in here, 4, half of that, so minus 2. And when I plug 2 in here, I get plus 4. All right, some good stuff's going to happen here. These 8s are gone.
So is it 2/3 square root?
This right here is going to cancel out with this one, right? And distribute this through. Well, let's just make this a 2, right? And then distribute. So 16/3 minus 2. That's where I'm at. Everyone follow that? 10/3? Ten-thirds. What do y'all think? Is that okay? Okay, look at example 3. Tell me what you notice about example 3. It's the same problem. So that's not a typo. There's a reason why we're going to do it again. All right, so we just had this picture. We just had this. Something like this. And we were trying to find the area in here, weren't we? And we did it. We got it, 10/3. But we had to break it up into 2 integrals. And the reason we had to do that is because there was a split where our top and bottom functions changed, didn't they? But that's because we were using a vertical rectangle. I want us to think about this in a different way now. What if I wanted to draw my rectangle horizontally like this? And we've never done this before. But let's think about this. If I take that rectangle and look at it over here, and this time I'm going to draw my y-axis. How wide is this thing?
Or f minus.
That's f of x, I think.
That, well, if I'm going to slide these rectangles up and down, then what variable is actually changing for me now? The y is changing instead of the x when I move it left and right. So that's going to be dy instead of dx, won't it? It'll be a change in y. Okay, so I'm going to call that dy. And then I need to know how wide this is, right? What I'm going to do is measure it. No, because it changes, right? As I move this, I think you said A to B. See, as I move this, the width of it changes, doesn't it? I want to look at this distance from the y-axis to here. And then I want to look at the distance from here to here. Well, we don't have that in any of the information that we have right now if we are fixated on looking at these as functions of x. If instead we look at them as functions of y, then you can look at that sideways. So let me write down the functions we had over here. Y is root x, and then y was x minus 2, right? What I'm trying to get you to see is this. These were both functions of x. We say that because if I plug in an x, it'll spit out the y value, won't it?
Right.
But what about the other way around? Is there a way to rewrite these two so that when you plug in y, it spits x out? You have to solve them both for x.
Oh, yeah.
For x. See, notice they're both solved for y right now? So you can get y, if someone gives you x, you know what y is. We want it the other way around. We want to know what x is if someone gives me y. So watch what I'm going to do. I'm going to take this equation right here, and I'd like for us to solve it for x. So how can you get x out of the root? Square both sides. Do you agree?
Yeah.
All right. And now what I can do is I can write something like this. F of y is y squared. See, our f function now is not a function of x, it's a function of y. If somebody gives me y, it'll spit out x. Right? Let's do the same thing for this one. Can you solve this? Oh, not that one. I don't want the g of x in there. I want just y. Can you solve that one for x?
Yeah, y plus 2.
Y plus 2 is x. That was easier to solve, right? Just add 2 to both sides. So now I can call my g function, g of y is y plus 2. You have to go back to college algebra and think about when we were looking at functions. This red thing right here, we would say is a function because it passes the vertical line test, right? So it is a function of x. Is it a function of y? Well, to do that, you have to look at a horizontal line test. Does the red curve represent a function of y? Yes, because it would, if you draw any horizontal line, it will only hit the red one time. Does the blue one pass as a function of x?
Yes.
How about a function of y?
Yes.
Yes, so it's your choice. You can look at both of those curves as either functions of x or functions of y. It's your decision. Understand? Now we do have some slight little issue here.
Yeah, it's y squared.
It's y squared, and y squared is a parabola. So if I were to graph right now, if I were to say, hey everyone, can you graph this relationship? You would draw me the whole parabola, wouldn't you? You would draw me this side of it also. So we have to understand that when we converted this over, we need to add one little tidbit of information to make sure our graph matches up there. And that's next to this, I'm just going to add one little condition. I'm going to say y must be greater than or equal to 0 for this one right here. That's telling me that my y coordinate has to be positive. That means I'm only going to draw, or 0. So I'm only going to draw this part of the red parabola. Pardon me?
I mean, I know it doesn't really matter because you already have a limit for the first one, but
This one doesn't present the same problem. See, if I ask someone to draw this one, it's going to draw the blue one exactly. And that's exactly what this one was. But if I ask someone to graph this one for me, it's not going to draw me the red one. It's going to draw me more than the red one. It's going to draw me this also. And that we don't want, you see? So we have to add that condition into it.
Isn't that a given though that it's not going to be negative? Because
No, the y coordinate's negative,
Yeah.
not negative.
yeah, isn't that a given though? Because anything squared is just
No. Think about this for a second. You're squaring the y coordinate,
Yeah.
and it spits out the x. So give me a y coordinate of -2. What do I get when I plug in -2 into this?
before.
I get 4. I get an x coordinate of 4, which puts me, well, it's supposed to be on there. You see? So it's backwards from what we've had before. Well, what I'm saying, though, is that I'm only allowing you to plug in 0 or positive y coordinates.
Give me where the bottom is.
So I'm only going to draw the top half.
So when we begin that condition prior, or we have to.
You would have to deduce that from the original problem, which was this.
Right.
Okay, you would have to realize that only draws me the top part. So if you're going to convert this into a function of y instead of a function of x, you cannot draw the whole parabola. You've got to restrict it.
Right, so like on the exam, you give us the original, say, in respect to y, and at that point, we have to make an assumption due to the, or
Yes.
according to the original.
Yes. Uh-huh. See, here's the danger. If you don't do this, then look, this is a different region, isn't it? The region bounded by these two curves includes this part also. And so that would create a problem. I mean, it wouldn't match the area we're going after, would it? All right, are y'all with me?
Because it's still, even though it still restricts on y is equal to 0 though, right?
Y, okay, so let's say we come in here now with y is 0. Right? If I see, this is why you have to cut that bottom piece off. If I do that, then which region are you talking about? This one up here or this one down here? Because this one down here is bounded by all of them, right? And this one up here. So do you mean both? So that last condition, y equals 0, doesn't really add anything to this problem, unless you cut this thing off. Then everything works out. Okay, so here, the distance from here to here is your f of y. And the distance from here to here is your g of y. So we've converted these over to functions of y instead of x. Now, what is the value of doing this? I mean, because we got it the other way, right?
One less step.
It's going to be one integral, right?
Yeah.
Because as I move this rectangle around, does the blue ever change on this side, on the right side? It's always the blue on the right, yes? And it's always the red on the left, no matter where I move that rectangle. So we're only going to have one rectangle. But everything is in terms of y now, right? dy, functions of y. So all my integrals should have y stuff in it. That means that my limits of integration, which are going to be, where these intersect, and also down here at this point, are actually y values instead of x values, because we want to move that rectangle up and down instead of left and right. So can you tell me where those are? First one's 0, right? Is that obvious?
2, and the other one would be 2.
How do you get 2 here?
So that would be a 4 before, right?
In the previous problem, it was 4, though, wasn't it?
But that's on the x-axis.
But it was on the x-axis.
Now it's on the y.
So on the y. But tell me how you're doing that. What we need to do is act like we didn't know it was 2.
So the correlation from the previous problem, we were speaking in terms of x, but we still had y and x there.
Yes.
We just reversed them. So it's like, I don't know, it's stereoisomer. Mirror image.
Yes, but I'm saying act like we didn't know it was 2 and 4,
Okay.
or 4 and 2. How would you do it algebraically?
Y squared equals y plus 2.
It's where these two hit each other, right?
Yeah.
So now you would set that up. I'm just giving you a way to do this, acting like we hadn't seen the previous problem. So if I want to know where this is, what I would do is I would find the intersection of y squared with y plus 2. And that's another quadratic, and you can move everything over and do your business on this. And you get 2 answers, 2 and -1. -1 is a solution, but it's not part of this. See that -1, do you see that it picked up this one right here? But see, that's not part of our region.
Is that where
'Cause
the
we
negative
restrict-
one came from?
No, the other one was because we squared both sides. So this is actually not an extraneous solution. This is a solution because this problem right here does not realize that you have cut half of it off. It doesn't know that. It's trying to find the intersection of a parabola and this line, and it's giving you the 2 y values where it happens. -1 down here and +2. But we only want the 2, right? All right, so let's set this integral up. I think we're ready. It should be the integral from 0 to 2. It'll be
Root x.
careful. Everything is in terms of y. Everything's in terms of y. So remember f was on top and g was on bottom? On the previous problem, f was on top, g was on bottom. If you're going to do this one, what you want to do is just turn your head sideways. And it's this is like the top and the bottom. If you want, the right and the left. Okay?
Oh, you always turn your head to the right?
To the right, just like this.
Every time.
Every time. Or you can just say right and left, whatever you want.
Even if you're working in the other quadrant with all negative functions, you'd still
Yes.
turn your head. Okay.
Yes. Yep. Good question. And the reason is because even if you had this over here, this is less negative than this one is. So. All right, so you ready? We're going to do
Y plus 2.
the line, right? The blue line is the one that's on the right side, which is y plus 2. And then the bottom one, which is the parabola, which is y squared. And we're differentiating with respect to y. Do you see what we've done? We've taken the same problem and we've converted it from vertical rectangles to horizontal rectangles, which means that our integration variable changes from x to y. This integral is easier to do than the previous one. Do you agree? I mean, they both are pretty easy, but this one
Just setting it up.
is just one integral, right? It's just one integral. Y plus 2 minus y squared. Let's integrate that. So
Basically, all the problems that we're going to do, there's going to be 2 ways to do them.
some of them, there are 2 ways. Some of them, you're forced to do it one way. So it'll just depend on the curves. Yeah. All right. So the reason why I do this one first is because I want to show you both ways. And we should get the same answer, shouldn't we? Okay, 1/2 y squared plus 2y minus 1/3 y cubed. 0, 2. I really like that because when I plug in 0, I know I'm going to zero everything out. So it's really just whatever I get when I plug in 2. 2 squared 4, half of that, 2. 4 minus 8/3. 6 minus 8/3.
18, yeah, it's 10.
It's 10/3. And that matches up, right? Same result. What you don't want to do is sit there and be like, you know what, I like the dx way better. Even though I had to do 2 integrals, I'm just going to stick to that. Because again, if you're given a problem where you're not given the choice, where you have to do it this way, you have to be prepared for it. So let's see if we can get one that we have to make the determination. There you go. So let's see what makes the most sense to you in this problem. Would you like me to let you try and set it up first?
Yeah.
Try and draw it, then try and set up the integral. I'll give you a few minutes.
You have to have all in one, right?
I'm sorry?
You have to have all in terms of one variable. You can't do line x.
Yeah, you can't mix it up.
approaching graphing all these correctly? If we wanted a sine wave, y is equal to x, and then two horizontal lines of pi over 2 and pi.
Something like that, yeah.
So then don't we have like one area here, another area?
It's got to be bounded by all those curves. So the first one you pointed at was only bounded by two of them. Yeah.
Okay. Alrighty.
You're on the right track. On the right track.
Wait, I think I might have gotten it wrong.
No, like,
This is
see how you
this is
have-
pi, this is
Well,
pi.
you see how you have y and those two variables?
Yeah,
But that
yeah,
was,
yeah,
the
yeah.
second one's stupid.
There you
The
go.
third and fourth, like you don't have minus, so you can't solve
this
for y.
makes
So
more
you have to
sense.
solve the negative. That's all.
Got a part there. Here's some check.
And I just, so I did arc sine.
Right, and then you know that half, so when you put a unit circle, half of it is pi, so and this gives it half, so that's pi. Right, and then half of pi would be pi over 2. Yeah. Like what I'm saying.
Yeah. That's not something.
There's so many unit circles. The unit circles like for real.
Maybe just be a horizontal.
That's just the only first one. All right, guys, so.
Y'all making any progress here?
Oh, yeah.
I think the biggest challenge in this problem is figuring out where x is, y equals x is.
Can you just do the work? Like a diagonal line?
Yes, but where is it in, I mean, because there's a lot of ways I could draw that. Like if I draw it like this, right? If I did, then the region enclosed by all of them is where? You know? If I draw it like right through that point, right? Then where's the region? If I draw it over here, like it needs to be accurate where it's positioned. So let's see if we can figure this out.
Won't the slope be affected by it?
Mhm.
Won't the slope be affected by it? Because if you're anywhere near it.
Yes, we can't just draw any lines. Y equals 1x, so the slope is 1, right? My question is, where is that relative to the sine curve?
I guess to that point,
What do y'all think? Where would, okay, so where would I be at pi over 2? If I plug pi over 2 into this function, where's my y value? Pi over 2. So what is pi over 2 as a decimal? Bigger than 1?
yeah,
Bigger than 1?
yeah.
So if I go out to pi over 2, I'm going to be bigger than this one. I know this is 1, right, because it's sine curve. The highest it's going to be is at 1 at pi over 2. I'm actually bigger than that, right? I'm up here somewhere? Yes? So when I draw this, I know it goes through the origin, like this. I know it's going to be something like that. Yes? And it goes up and hits up there somewhere. Yes?
That is,
Does that give you a region enclosed by all 4?
Yes.
Where is it?
right there?
That little piece?
No.
No, that's only enclosed by 2. This one?
No.
No.
It's enclosed by 3 of them.
And then the.
No.
This one right here?
Yeah.
This is enclosed by all 4. Got it? Now, would you like to do vertical rectangles and keep everything in terms of x? Or would you like to do horizontal rectangles and do everything in terms of y? And give me some justification as to why.
Then it's just going to be,
Yeah, it's
That's what it is.
vertical.
If you do vertical, what's going to be the top function? The whole time it's going to be the red y equals x, right?
yeah,
And the whole time the bottom one is going to be
black
sine, right? And then your left endpoint of integration would be pi over 2, and the right one would be pi. That looks pretty clean.
Yeah.
If you go this way,
You have to do 2
up here, yeah, you've got the one on the right is this one, and then it's this, until we get to about here, and then it switches from here to this. Then when we get to the black curve, it's going to switch from the red to the black. Do you see there would be 3 different integrals that way?
Yeah.
I'd prefer not to do it that way. Wouldn't you? So vertical rectangles, vertical slices. So I'm going to draw a vertical rectangle in here. Like that. Over here on the side, I'm just going to draw it again, just because I like to. This is not part of the same picture. I'm just trying to get a feel for what's happening over here. Got a rectangle. I know on top, it's always going to be y is x. And I know the bottom is always going to be that sine curve, right? Y is sine x. Do you see how I'm doing this? I'm doing this to try and help us see what our top and bottom functions are going to be. Are y'all ready to set the integral up?
Yeah.
We didn't have to find an intersection here, did we?
No.
We got kind of lucky with that. So I'm going to go integral. Where? Pi over 2 to pi. And then top function x minus sine x. Don't really need all these parentheses. I'm just getting into the habit of putting them there. And that's it.
And take the antiderivative.
Find the antiderivative and go from there. So I'm going to say at this point, dot, 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 which means you could do that on your own. Not right now, though. That's the setup of the integral. Are we good? Questions? No? You're all right? Okay. The spring break cobwebs. There's the picture. See, if I show you the picture first, it's a lot, it's too easy because it's not realistic. You've got to be able to get this picture. That's part of the challenge. All right. Try that one. Give you about 10 minutes. I'm going to step out for 10 minutes. I'm going to see what you do, and when I come back, I'm going to see if y'all have made any progress. No. That problem's too easy. I'll give you a harder one. I'm kidding.